Space is awe-inspiring. It's vast, mysterious, and wildly misunderstood. For decades, we've filled the void with science fiction, half-truths, and flat-out myths. But the real universe? It's far stranger and more mind-blowing than anything you were taught in school. So, sit back, relax, close your eyes, as we help you drift off into a cosmic slumber. Myth number 1. People explode in space. It's one of the most dramatic and deeply rooted images in pop culture. A human body, unprotected in the vacuum of space, instantly inflating like a balloon before violently bursting. No spacesuit, no hope. 1 second you're alive, the next you're a cloud of red mist. It's terrifying, it's cinematic, and it's completely wrong. But what actually happens when a person is suddenly exposed to the vacuum of space? The truth is far more disturbing and far more fascinating. First, let's understand what space really is. Outer space isn't just empty, it's a vacuum. No air, no pressure, no oxygen. It's the closest thing to nothing our universe can offer, and our bodies, intricate machines fine-tuned by millions of years of evolution, are built entirely for Earth, a place with atmosphere, pressure, gravity, and breathable air. Remove those, and things go south, fast. If you were suddenly ejected into space with no suit, you wouldn't explode. Your skin is elastic and strong enough to hold your body together. There's no internal detonation, no bursting limbs. But what you would feel is your body rebelling in ways that are hard to imagine. The moment you're exposed, the air in your lungs becomes your biggest threat. If you held your breath, the air trapped inside you would rapidly expand. Your lungs could rupture from the pressure difference, forcing gas into your bloodstream, a deadly condition known as an air embolism. That alone could kill you within seconds. This is why astronauts are trained to exhale during sudden depressurization. As the pressure around you drops to zero, any liquid exposed to the environment starts to boil. Not from heat, but because there's no pressure to keep it stable. The saliva on your tongue bubbles. The tears on your eyes begin to vaporize. The moisture in your nose and throat hisses into gas. It's a sensation no human has experienced consciously and lived to describe. Internally, your blood is safe from boiling thanks to the containment of your circulatory system, but the lack of oxygen causes immediate problems. Within 10 to 15 seconds, you lose consciousness due to hypoxia, oxygen deprivation. You wouldn't feel much after that. Your brain would fade into blackness, unaware of what was happening next. In those final moments of consciousness, you might experience swelling. Without external pressure, the nitrogen dissolved in your blood forms bubbles, similar to decompression sickness. The bends. Your skin and soft tissue could puff up, distending your body to twice its normal size. But you wouldn't pop. You'd simply bloat, like a balloon filled with too much air. Painful, yes, but not explosive. And then comes the cold. In space, there's no air to conduct heat, so your body wouldn't freeze instantly. Instead, you'd slowly radiate heat into the vacuum. It could take hours for your body temperature to drop enough to freeze, depending on where you are. In shadow, near absolute zero. In sunlight, you might actually burn. Space can be both freezing and scorching, depending on exposure. There's one real-life example worth mentioning. In 1966, during a test at NASA's Johnson Space Center, a technician inside a vacuum chamber accidentally lost pressure in his suit. he was exposed to near-space conditions for about 15 seconds before being rescued. He remained conscious for about 12 seconds, just long enough to feel the saliva on his tongue start to boil, before passing out. He survived. That incident remains one of the most valuable data points we have about what truly happens to an unprotected human in space. So no, you wouldn't explode, but you would experience something far more alien. You'd float, helpless, bloated, unconscious, and dying in silence, surrounded by the most beautiful, indifferent environment in existence. The stars would shine without flickering. The Earth, if visible, would look achingly close, and time would slow to a crawl in your final moments, not literally, but in the haunting realization that this is what it feels like to leave the only world we were ever meant to live on. What's truly terrifying isn't how violent space is. It's how calm it is while killing you. Myth number 2. Space is completely silent. You've heard the phrase, "In space, no one can hear you scream." It's one of the most iconic taglines in film history, and it's scientifically accurate, but only part of the story. Because while space is a vacuum, and sound as we know it can't travel through emptiness, the idea that space is silent, utterly, forever mute, misses something far more profound. Let's start with the science. Sound requires a medium. On Earth, that medium is usually air. Molecules bumping into each other, transmitting vibrations to your eardrum. In water, sound travels even faster. But in the vacuum of space, there are no molecules to carry the vibration. If you were floating outside the International Space Station and someone detonated a stick of dynamite beside you, assuming you somehow survived, you wouldn't hear a thing. Not a boom, not a bang, not even a whisper. The explosion would play out in perfect silence. But here's the twist. Space is not devoid of energy. It's not quiet in the way we imagine silence, as a total absence. Space is alive with radiation, charged particles, electromagnetic fields, and plasma waves. Stars pulse, galaxies spin. Magnetic storms rage across the surfaces of suns. There is motion in the silence, and where there is motion, there is vibration. We just needed the right ears to hear it. Using instruments like the Voyager spacecraft and NASA's Chandra X-ray Observatory, scientists have begun converting electromagnetic vibrations and plasma fluctuations into audible sound waves, a process known as sonification. What we've heard is nothing short of breathtaking. Saturn emits eerie radio emissions that sound like ghostly wails. The Sun sings a deep, persistent rumble that vibrates across its surface. And black holes groan. In 2022, NASA released an audio clip of a black hole located 250 million light-years away in the Perseus galaxy cluster. When the pressure waves from that black hole were translated into the range of human hearing, the result was haunting. A low, moaning howl, as if the universe itself were in pain. It's not a sound you'd hear with your ears, but it's there, rippling through hot gas and magnetic fields, waiting to be transformed into something we can feel. And that's where this myth unravels. Space isn't quiet, not in the way we imagine. It's filled with frequencies we can't hear, with energy we can't see. It's a symphony without a conductor, playing notes far beyond human range. The silence of space is not empty. It's simply outside our grasp. Think about it. The universe is vibrating, right now. Galaxies hum, pulsars beat like cosmic metronomes. Even the background radiation left over from the Big Bang still echoes faintly across the cosmos. We exist in a sea of motion, a silent storm of physics and time. So yes, in space, no one can hear you scream, but only because you're listening with the wrong instrument. The universe is not silent, it's singing, we're just learning how to hear it. Myth number 3, the moon has a dark side. It sounds ominous, mysterious, even a little poetic. The dark side of the moon, a hidden hemisphere forever cloaked in darkness, untouched by sunlight, unreachable by man, the stuff of sci-fi legends, conspiracy theories, and album covers. But here's the truth. There is no dark side of the moon, not in the way most people imagine it. The myth comes from a real phenomenon, tidal locking. The moon orbits Earth in such a way that it always shows us the same face. If you've ever looked up at a full moon, the features you saw, the dark seas of hardened lava, the bright streaks of ancient impact scars, are the same features every human has seen from Earth for tens of thousands of years. That familiarity creates the illusion that the moon simply doesn't turn. But the moon does rotate. It just does so at the exact rate it revolves around Earth. That delicate dance means one side always faces us, and the other, the so-called dark side, faces away. But it's not dark. In fact, every part of the moon gets sunlight over the course of its 29.5-day cycle. The far side experiences day and night just like the near side. It's just hidden from our view. Still, this far side of the moon remained mysterious for centuries. Until 1959, no human had ever seen it. That year, the Soviet spacecraft Luna 3 snapped the first photos of the moon's hidden face. What we saw shocked scientists. The far side looks drastically different. It has fewer of the dark, smooth plains called Maria and far more craters. It's rougher, more ancient, almost alien. Why the stark contrast? One theory is that Earth's gravity subtly influences the distribution of molten rock on the near side, smoothing it over eons. Meanwhile, the far side, untouched by that pull, bears the scars of a billion-year bombardment, preserved like a fossil record of the solar system's most violent days. Today, we've not only photographed the far side, we've landed there. In 2019, China's Chang'e 4 mission became the first spacecraft to soft land on the moon's hidden hemisphere. It carried instruments, a lander, even a tiny biosphere with seeds and insects. For the first time in human history, we were doing science in a place once considered forever unknowable. So no, the far side of the moon is not a dark, frozen void. It's a sunlit, cratered frontier, a landscape sculpted by cosmic time. And ironically, it may hold the key to our future in space. Astronomers dream of building radio telescopes on the far side, shielded from Earth's noisy signals, where we could finally listen to the faint whispers of the universe, undisturbed. The real story isn't that the moon has a dark side. It's that we assumed it did, because we couldn't see it. And for so long, we equated unseen with unknown. But as we've learned over and over again in space exploration, darkness is never the absence of light. It's the beginning of discovery. Myth number 4. Space travel disproves evolution. It's a strange claim, one you might hear in internet comment sections or whispered among conspiracy circles, that human beings weren't meant for space, and our inability to thrive there naturally proves we didn't evolve on Earth. That evolution itself must be flawed, or worse, fabricated. But this myth doesn't just get science wrong. It overlooks one of the most awe-inspiring truths about humanity, our ability to adapt far beyond what nature ever required. First, let's set the record straight. Evolution is not about perfection. It's not about comfort. It's about survival, moment to moment, generation to generation. Life doesn't evolve towards some ideal form. It adapts to fit its environment just well enough to persist. And Earth has been our environment for hundreds of thousands of years. Gravity, atmosphere, a protective magnetic field. It shaped everything about us, from the curvature of our spines to the viscosity of our blood. So, yes, when we step off this planet and into the void, our bodies falter. In microgravity, bones lose mass. Muscles atrophy. Fluids shift to the upper body, causing puffy faces and pressure in the skull. Vision changes, hearts reshape. Even the immune system behaves differently. From the outside, it may look like our biology is breaking down. But that breakdown tells a deeper story. It shows just how finely tuned we are to Earth. And more importantly, it reveals how incredibly fast our bodies respond to new extremes. Within days of entering space, an astronaut's physiology begins adjusting. Genetic expression changes. Neural pathways rewire. Our cells, confused by weightlessness, begin experimenting with new ways to function. We adapt, not perfectly, not permanently, but faster than almost any other species could. This is evolution in real time, not over generations, but within one lifetime. And when astronauts return to Earth, many of these changes reverse themselves. The body remembers home, but each mission teaches us something new about the limits of that memory, and how we might one day evolve to call space our permanent residence. In fact, scientists are already studying the possibility of using artificial gravity, gene therapy, and biomechanical augmentation to support long-term life off Earth. We're not helpless in space. We're just in the early chapters of learning how to write new instructions for the human body. And here's the real irony of this myth. Space travel doesn't disprove evolution. It proves how essential it is. The very need to adapt, the ability to change under pressure, is the core of evolutionary success. Every time we send a human into orbit, every time we stretch our biology to match the unforgiving contours of the universe, we're not stepping outside of evolution. We're pushing it forward. So no, space doesn't reveal that we're strangers in the cosmos. It reveals that we're survivors, explorers, the only known species on this planet to look up at the stars and say, "Let's go there." And then, incredibly, to start building the means to do it. Myth number 5. You can't cry in space. You might have heard this one before, that crying in space is impossible, that astronauts, no matter how emotional they get, can't shed tears in orbit. It's the kind of claim that feels symbolic, as if space is so cold, so hostile, that it won't even let you grieve. But the truth is more human and more haunting. You can cry in space, but it's not like anything you've experienced on Earth. Here on the ground, gravity gives tears a direction. They form, swell, and fall, slipping down your cheeks like tiny liquid parachutes pulled gently by the planet. But in microgravity, tears don't fall. They don't go anywhere. They collect, they hover, they cling. When astronauts cry aboard the International Space Station, their tears form a glistening bubble that sticks stubbornly to the eye. Each tear joins the last, building up into a watery sphere that distorts vision, blurs the world, and sometimes stings the skin. There's no natural drainage, no relief. The only way to wipe them away is to physically remove them, brushing them aside with a tissue or letting them float off into the cabin, where they drift like tiny glassy satellites. But here's where it gets even more profound. Astronauts do cry in space. Not often, but it happens. Sometimes it's from physical discomfort, like the stinging sensation caused by fluid buildup in the face. But more often, it's emotional. Floating above Earth, watching the blue marble spin silently below, realizing how thin the atmosphere really is, how fragile life is, how small we are in the cosmic scale, it hits you. Veterans call it the overview effect, a kind of spiritual collapse and rebirth. The sudden clarity that Earth is one shared, living organism, suspended in darkness, without borders or backup. And when that clarity sets in, tears come. But space makes those tears strange. They don't fall. They just stay with you. A perfect metaphor for the weightlessness of it all. You're crying, but the sadness doesn't land anywhere. It floats. It lingers. Astronaut Chris Hadfield once described it like this: your eyes make tears, but they don't fall down your cheeks. They just form a big ball of liquid on your eye, and it makes your eye sting. You have to wipe them away with a cloth. And yet, what's remarkable isn't the inconvenience. It's the fact that even in one of the most extreme environments we've ever ventured into, our emotions remain intact. Space doesn't strip away your humanity. If anything, it amplifies it. Up there, far from everything you've ever known, the emotional core of what it means to be human, love, fear, awe, grief, floats with you. So yes, you can cry in space, but your tears won't fall. They'll hover, weightless, like your thoughts, suspended in a place where physics and feeling meet, quietly orbiting the edges of who we are. Myth number 6. The Great Wall of China is visible from space. It's one of the most repeated facts in the world, told in classrooms, trivia nights, and even some textbooks. The Great Wall of China is the only man-made structure visible from space with the naked eye. It sounds incredible. A monument so vast, so enduring, that it can be seen from orbit, standing alone among the clouds and continents, whispering across time. But as beautiful as that story is, it's a myth. In truth, you can't see the Great Wall from space, at least not with the unaided human eye. Even astronauts themselves have tried. Most say the same thing. It's nearly impossible to pick out. Why? Because the Great Wall, while long, stretching thousands of miles, is relatively narrow. Its materials are earth-toned and weathered, blending into the natural landscape. From low Earth orbit, where the International Space Station orbits at around 250 miles above the surface, it simply disappears into the background noise of valleys, hills, and shadows. It's like trying to spot a hairline scratch on a vast slab of granite. So where did the myth come from? It likely dates back centuries, long before spaceflight, when people imagined that something that massive must be visible from the stars. The first time it was seriously written about was in 1938, in a second-hand claim. Then, when the space age began, it slipped into pop culture and stuck. In reality, there are many man-made structures you can see from space, and they're not what you'd expect. Major highways, brightly lit cities, massive airport runways, solar farms, agricultural grids cutting geometric shapes across entire regions. At night, Earth glows like circuitry, pulsing with human activity. But the wall, it hides in plain sight, and that's what makes the truth even more profound. The myth says we can see the Great Wall from space. The reality is, what we can see is a species that has transformed an entire planet, not with one monument, but with billions of interwoven lights, roads, cities, dams, and farms. Humanity hasn't built one giant thing visible from orbit, we've built everywhere. Even still, the wall remains iconic, not because it's visible from above, but because it connects us to a time before rockets, satellites, or orbit, when space was just the sky above our heads, and the wall was the boundary of an empire, and imagination was the only way to explore the stars. So no, the Great Wall of China isn't visible from space, but that doesn't make it less impressive. If anything, it reminds us that the most powerful stories aren't always the most accurate. They're the ones that make us look up. Myth number 7. The sun is yellow. Since childhood, we've been taught to color the sun yellow. Bright golden rays, smiling cartoon faces, the warmth of a summer afternoon. Yellow just feels like the color of the sun. We've seen it with our own eyes, glowing at noon, dipping orange at sunset, blinding white at its peak. And so the myth took root. The sun is yellow, but it's not. Not in space, not in truth. If you were to stand outside Earth's atmosphere, hovering in the vacuum beyond the scattering air and dust, and look at the sun directly, though please don't, you wouldn't see yellow. You'd see white, brilliant, clean, overwhelming white. Here's why. The sun emits light across the entire visible spectrum, from red to violet, and beyond, into ultraviolet and infrared. It radiates every wavelength in near-perfect balance. That makes it what physicists call a G-type main sequence star. But more importantly, it makes its light white, equal parts all colors, shining in harmony. So why do we see it as yellow from the ground? Because Earth gets in the way. Our atmosphere is like a filter. As sunlight enters, it collides with molecules in the air, scattering the shorter, higher frequency blue and violet wavelengths more than the longer reds and yellows. That's why the sky appears blue. The blue light is bounced around in all directions. Meanwhile, what's left, especially when the sun is low on the horizon, is a palette of warm hues: gold, amber, red. Our sunsets are not the sun's true color. They're a gift from our atmosphere, and a reminder that perception is shaped as much by where you stand as by what you're looking at. In space, without this veil, astronauts describe the sun as a harsh, white fire. Not soft, not warm, just raw, blinding energy. And yet it's that white-hot brilliance, that balanced storm of radiation that gives us everything. It fuels photosynthesis, it powers winds and waves, it keeps oceans liquid and atmospheres alive. Everything that moves, breathes, grows and dies on this planet owes its existence to that burning fusion engine 93 million miles away. So no, the sun isn't yellow, not really. But maybe the myth says something deeper. Maybe we see the sun as yellow because we associate it with warmth, with life, with safety, because colouring it white feels too clinical, too cold, too honest. But that's what science gives us, not a less beautiful world, but a more accurate one. One where the truth is not only stranger than fiction, it's brighter. Myth number 8. There's no gravity in space. We've all seen it. Astronauts floating effortlessly in their spacecraft, gliding through airless chambers like underwater dancers. We call it zero gravity, and the phrase has burned itself into pop culture. Movies show tools floating, tiers hovering, entire crews drifting silently, weightless. So the myth seems obvious. There's no gravity in space, but in reality, gravity is everywhere, inescapable, unrelenting. It's one of the most pervasive forces in the universe, and space is soaked in it. Here's the truth. Astronauts don't float because gravity disappears. They float because they're falling. Let's break that down. Gravity is what keeps the moon orbiting Earth, Earth orbiting the sun, and the entire solar system tethered to the spiral arms of the Milky Way. Even at the altitude of the International Space Station, about 250 miles above Earth's surface, gravity is still roughly 90% as strong as it is on the ground. The difference isn't the presence of gravity, it's the experience of it. Astronauts float because they're in continuous free fall. The space station and everything in it is falling toward Earth. But it's also moving forward so fast, nearly 17,500 miles per hour, that it keeps missing. That perfect balance of speed and pull creates an orbit. Like a coin rolling around the rim of a bowl, they're trapped in a loop of perpetual descent. Inside the station, everything, astronauts, tools, drops of water, even the air, is falling together. There's no resistance, no downward force, so everything appears to float. It's not that gravity is gone, it's that you're sharing the fall together. It's the same sensation you get for a moment on a roller coaster, or when an elevator drops, that brief flash where your stomach lifts and the ground seems to vanish. Now imagine that feeling never ends. This weightlessness, more accurately called microgravity, is what allows astronauts to study physics, biology, and the human body in ways we can't on Earth. But it comes at a cost. Bones lose density, muscles shrink, fluids shift to the head, even the heart begins to weaken. Because evolution built us for gravity. Every heartbeat, every joint, every nerve in your inner ear is calibrated to fight Earth's pull. Remove that pull, and your body begins to rewire itself, sometimes in beautiful ways, sometimes in alarming ones. But here's the most awe-inspiring part. This illusion of weightlessness is what gives us perspective. That serene, floating astronaut, they're not defying gravity. They're in its grip completely. They're riding a force so powerful it holds moons in orbit and bends the path of light itself. Gravity isn't absent in space. Gravity is space. It shapes everything. It's why there are stars, why there are galaxies, why you exist. So the next time you see an astronaut drifting, remember, they're not free from gravity, they're dancing with it. Myth number 9. We've explored most of our solar system. In the age of high-resolution Mars rovers, Voyager spacecraft cruising past Neptune, and AI-generated renderings of distant planets, it's easy to feel like we've been there, that the solar system is mapped, charted, known, just waiting for us to pack a bag and go. The myth says, we've already explored most of it, but the truth, we've barely scratched the surface. Let's start with a simple number. As of now, only 12 human beings have ever left Earth and stepped onto another world, and all of them went to the same place, the Moon. That's it. No one has ever walked on Mars. No one's even orbited another planet. Everything else we know comes from flybys, robotic landers, remote sensing, and telescope data. We've sent spacecraft past Mercury. Probes have orbited Venus, skimmed Jupiter's storms, even threaded the rings of Saturn. But most of these missions were just that, flybys, moments in time, snapshots. we've only landed on a handful of planetary bodies. Mars, a few rovers scattered across an alien desert. Titan, a single probe that parachuted down, snapped some photos, then went silent. Europa, Ganymede, Enceladus, moons that may hide oceans beneath icy crusts, remain untouched. Not a single grain of dust has been scooped from their surface. And then there's what lies beyond. Beyond Neptune lies the Kuiper Belt, a vast frozen graveyard of dwarf planets and icy bodies left over from the formation of the solar system. Pluto is just one of them. There are others, Eris, Haumea, Makemake, worlds that twist and tumble in eternal twilight, orbiting a sun that's little more than a bright star in their sky. We've visited one of them, Pluto, for a few hours in 2015 as NASA's New Horizons spacecraft raced by at 36,000 miles per hour. No lander, no orbit, just a glimpse. And beyond the Kuiper Belt lies something even more mysterious, the Oort cloud, a theoretical shell of icy bodies that may encase the entire solar system like a ghostly bubble. It could contain trillions of comets stretching a light year from the sun. No spacecraft has ever seen it. None likely will in our lifetimes. But it's part of our solar system too, and right now it's a shadow in the dark. Even the planets we think we know hold secrets. Mars may still hide liquid water underground. Venus might be geologically active. Uranus and Neptune, two ice giants that have been visited only once in passing, may harbour violent storms, unknown moons, and magnetic fields that defy explanation. The truth is this: when it comes to the solar system, we are still at the shore, staring into a cosmic ocean. And maybe that's the most exciting part. We haven't explored it all, not even close. But we're building the tools. We're sending new missions to Europa, to the asteroid belt, to Mars, again and again. One day, we'll leave footprints where only dust has settled for billions of years. The map is mostly blank, and that means the age of exploration isn't over, it's just beginning. Myth number 10. Black holes suck up everything. The name alone is a warning. Black hole, a cosmic monster that swallows stars, a gravitational death trap, a rip in space that devours anything and everything that gets too close. The myth says black holes are like vacuum cleaners, roaming the galaxy, sucking up planets' light, time, and maybe us. But the reality, black holes are powerful, yes, but they don't defy the laws of physics. They are the laws of physics, pushed to their limits. First, black holes don't suck. They pull, just like anything else with mass. The only difference is, they pull really hard. If our sun were magically replaced with a black hole of the same mass, Earth's orbit wouldn't change. We'd keep circling, same path, same speed, just colder, darker, and very dead. What makes black holes dangerous isn't that they defy gravity, it's that they concentrate it. Imagine compressing a star several times more massive than the sun into something the size of a city. That density curves space so sharply that not even light, the fastest thing in the universe, can escape. That's what a black hole is, not a hole, not a vacuum. A collapsed star so heavy it folds space inward like a trapdoor. But here's where it gets even stranger. Approach a black hole and time itself begins to slow. Not metaphorically, literally. To a distant observer, you would fall slower and slower, your movements grinding to a halt as you approach the event horizon, the point of no return. You'd seem frozen in place, like a ghost on the edge of forever. Meanwhile, to you, time would pass normally. until gravity stretches you like spaghetti, tearing atoms apart. Scientists call this spaghettification. It's not science fiction. It's what happens when you cross the horizon. You don't get crushed, you get unraveled. And yet, even with all this, black holes are not galactic predators. They don't roam, they don't hunt. They form when massive stars die, leaving behind scars in the fabric of reality. Some sit quietly in the centers of galaxies, invisible until a passing star or gas cloud strays too close. Then they flare, releasing X-rays, jets of matter, flashes of light from the edge of darkness. And inside, we don't know. At the heart of every black hole is what's called a singularity, a point of infinite density where the rules of physics break down. Time, space, gravity, all cease to function in ways we can understand. Some theories suggest black holes may lead to wormholes. Others hint they could be gates to new universes. But for now, it's just speculation. Black holes don't suck up everything. They're not villains. They're endpoints. And maybe, just maybe, beginnings. The universe hides its most profound mysteries inside them, and the fact that they exist at all is a reminder. Space doesn't just stretch imagination, it shatters it.